You've landed dozens of times, maybe hundreds, and every single time you've probably watched that moment. The wheels dropping out from under the plane, that mechanical clunk, the ground rushing up, and never once thought about what's actually inside those tires. You know, what's in your car tires? Air. Everyone knows that. You pump them up at the gas station, maybe check the pressure once a year if you're responsible, and that's it. So, naturally, you'd assume a plane tire is just a bigger version of that. Same idea, different scale. Here's the thing. Airplane tires don't use air at all. And the reason why is going to change how you think about every landing you've ever survived. Why would something as simple as air be completely off the table? What's actually inside them? Why do these tires go from totally still to 250 kilometers an hour in less than a second and not explode? Why does a 747 need 18 wheels? And what actually happens if one of them blows out right as the plane touches down? Let's go. The most violent mechanical event of your entire flight doesn't happen at takeoff. It doesn't happen in turbulence. It happens the moment the wheels touch the runway. Think about what's actually going on in that split second. The tires are not spinning before the plane lands. They're sitting still, completely stationary. Then they hit asphalt at over 250 kilometers an hour and have to go from 0 to full speed almost instantly. Not because the engine drives them, but because friction does. That's not a gentle ramp-up. That's a violent, instantaneous spin-up driven entirely by the runway grinding against the rubber. That white puff of smoke you've seen in landing videos? That's not something going wrong. That's the physics of a dead-still tire catching up to 250 kilometers an hour in a heartbeat. That's exactly what it's supposed to look like. Now add the weight. A fully loaded commercial jet can land at 300 to 400 tons. That's roughly the same as stacking 250 to 300 average cars on top of each other and dropping them from the sky onto a strip of rubber. And the forces aren't only going straight down, there's also the horizontal drag of deceleration, the plane pushing forward while the tires are screaming to slow it down. All of that happening at once in the first fraction of a second of contact. So, the question isn't why these tires are special. The question is how they survive at all. Here's the part most people miss. These are not large versions of car tires. They are completely different objects. A car tire is mostly rubber with some steel and fabric inside for shape. An airplane tire is built more like armor. Inside the rubber, there are multiple layers of reinforcement made from industrial nylon and aramid fiber, the same fiber family used to make Kevlar vests. It's not just thick rubber. It's a tightly engineered structure designed to hold its shape under extreme force without cracking, bending, or tearing apart. And then there's the pressure. Your car tire probably runs at around 30 to 35 psi. That's pounds per square inch, the unit used to measure how hard the gas inside is pushing against the walls. An airplane tire runs at around 200 psi. That's not a little more. That's 6 times higher. Picture squeezing a water balloon until it's almost rigid. That's closer to what's happening inside an airplane tire. The high pressure is what keeps the shape locked even when 400 tons of airplane is sitting on top of it. Before any of these tires ever touch a real runway, they go through certified testing, simulated high-speed, max-load landings in a lab. They're not legal to fly until they pass. So these tires don't survive landings by luck. They're legally required to. But here's where it gets crazy. If pressure is what holds everything together, why not just fill them with compressed air? That's what pumps do. That's what gas stations use. That's what makes sense. Except, air is not a simple thing. Air is a mixture. About 21% of it is oxygen, a gas that reacts with other materials under heat. And all the rest is mostly nitrogen, plus water vapor, which is moisture hiding inside every breath of regular air. That moisture is the problem. Think about the temperature range a tire lives through in a single flight. On the ground, it's a normal day, maybe 25 degrees Celsius. At cruising altitude, the outside temperature can drop to -50. Then the plane descends and lands, and the carbon brakes, which we'll get to in a moment, can briefly reach over 1,000 degrees Celsius. That's hotter than most lava. Put moisture inside a container that swings through that temperature range multiple times a day, and the pressure behavior becomes impossible to predict. It spikes, it drops, it surges at the wrong moment. In aviation, an unpredictable pressure spike is more dangerous than a high pressure. Predictability is the whole point. So they use dry nitrogen, Pure, dry nitrogen. No oxygen, no moisture. Nitrogen is inert, meaning it doesn't react with other materials. It doesn't corrode the inside of the tire. It doesn't carry water vapor. When it heats up, it still expands. That's just physics, the same for any gas. But because there's no moisture mixed in, that expansion is smooth, steady, and completely predictable, every time, under any conditions. Ground crew knows exactly what pressure to expect. Engineers know how the tire will behave. Nothing is a surprise, and in aviation, no surprises is the goal. Now, back to the question about all those wheels. Most people, if they picture a plane, assume it has something like 4 to 6 wheels, similar to a big truck. But a Boeing 747 has 18 wheels. The Antonov AN-225, the largest cargo plane ever built, had 32. That's not excessive. That's math. Take 400 tons and divide it across 18 contact patches instead of 4. Each individual tire carries a fraction of the load. Each section of runway underneath absorbs a fraction of the impact. Without that distribution, the runway surface would need to be rebuilt to a much heavier standard just to survive regular landings. Multiple wheels also mean redundancy. If one tire fails, the others immediately absorb the difference. The plane doesn't tip. The structure doesn't shift. It keeps going, which leads directly to the question everyone wants answered. What happens if a tire actually blows out on landing? Unlike a car tire blowout at highway speed, which can send you spinning into a barrier, an airplane tire failure is something engineers specifically design for. And certification rules require that a commercial aircraft must be able to land safely even with a failed tire. The reinforced structure of aviation tires means they don't explode into fragments the way a car tire might. The carcass usually holds its shape well enough that the wheel still rolls. Load shifts to the neighboring tires instantly and passively, with no input needed from the pilot. Real landings have been completed successfully on damaged tires. This is documented. Safety in aviation isn't built on the hope that nothing goes wrong. It's built on the assumption that something eventually will. And the tires aren't done working after touchdown. The moment the wheels are spinning at full speed, the braking system takes over, and the tires are part of that too. Commercial planes use carbon brakes, a material capable of handling extreme heat, sometimes above 1,000 degrees, that builds up during a hard stop or a rejected takeoff, when the pilot aborts right at full speed. At the same moment, spoilers on the wings pop up to reduce lift, pushing more weight down onto the wheels so the brakes bite harder. Thrust reversers redirect engine force forward to help slow the jet. 3 systems firing at once, wings, engines, and brakes, all working together while the tires hold everything to the ground. The tire isn't the whole system, but without it, none of the rest works. Here's something worth knowing about where all this came from. Early planes did use regular compressed air, the same way you'd inflate a bicycle tire. And for a while, that worked fine. Planes were lighter, slower, and didn't push tires to the extremes they handle today. But as aircraft got heavier and faster, the moisture problem got worse. Pressure inside the tires became unpredictable. Blowouts happened more often than anyone was comfortable with. By World War II, military ground crews were already experimenting with alternatives. According to some accounts from Pacific Theater maintenance records, mechanics on remote island airstrips would occasionally drain tires and refill them with CO2 from on-site fire suppression cylinders when nitrogen wasn't available, just to get a drier, more stable gas inside before the next mission. It's presented as a version, not a certainty, but the underlying problem it was solving was real. After the war, as commercial jet aviation was being built from scratch in the 1950s, dry nitrogen became the certified standard across the industry, not as a premium upgrade, as the baseline. Now, none of this is permanent. A commercial aircraft tire lasts roughly 100 to 300 landings depending on the plane, the runway conditions, and how hard the pilot sets the plane down. After that, the tire gets pulled. But the carcass, the internal structure of aramid and nylon, often gets a second life. A new rubber tread is bonded onto the old frame under strict aviation certification standards. Basically the same concept as retreading a truck tire, just with a lot more paperwork and testing. The individual tire itself doesn't cost a fortune, a few hundred to a few $1,000s, depending on the aircraft type. The real cost is the logistics, tracking every tire, counting every landing cycle, scheduling inspections before problems appear. Newer aircraft are starting to address that with embedded sensors that track real-time pressure, temperature spikes after landing, and cumulative cycle counts. Some systems in development aim to send that data to ground crews while the plane is still in the air, so the maintenance team is ready before the wheels even stop rolling. You've been watching all of this your entire flying life without knowing it. That smoke puff on every landing video you've seen, that's 0 to 250 in 1 second. That thud you feel in your seat, that's 6 times your car tire's pressure, taking the hit so you don't have to feel it worse. That ordinary-looking tire you walked past on the nose gear at the gate, filled with industrial nitrogen, not a gas station compressor. The fact that the runway didn't crack under the plane you arrived on is partly because 18 wheels spread that load, so no single point got too much. Every safe landing you've ever had involved carbon brakes briefly reaching temperatures close to what flows out of a volcano. The ground crew moving around under the plane after parking. One of their jobs, every single time, is visual tire inspection. The reason you've never once boarded a flight and heard, "We have a tire issue," isn't luck. It's because the people who built this system assumed the worst-case scenario first, then designed so it wouldn't matter. Those tires you've never thought about are among the most tested, most monitored, most deliberately engineered objects on the aircraft. And the runway they land on? That's its own story, built specifically to handle failure. Not just withstand it,